for the non-homogeneous system of equations, which means that for your right hand side at least one of b1, b2, bn is non-zero. Let's see how to solve this. So the general matrix representation is Ax equals b. So pre-multiply it by A inverse. So A inverse times A times x equals A inverse times b. You have to do the operation on both sides of the equation to keep the relation the same. And provided A inverse exists, then you will recognize this part, A inverse times A, as the identity matrix of order n equals A inverse times b. And any matrix multiplied by identity is just itself. So that gives us the solution A inverse times b, provided A inverse exists. So that is adjoint of A over determinant of A times b. So this is the method to find the solution of a set of linear equations in n unknowns. Now there are some special cases. So this thing works fine if the determinant is non-zero. Now what happens if the determinant is 0? So the special case, if determinant of A is 0, look at the numerator of this expression. If adjoint of A times b, if this product is not 0, the system of equations, this whole system of equations is inconsistent and it has no solution. But if the numerator is also 0, in addition to the denominator being 0, then the system is consistent and it has an infinite number of solutions. Okay, so this is one way using matrix operations to solve a system of simultaneous linear equations. A second way is using determinants, or what is known as Cramer's rule. For the same system of equations Ax equals b, the solution for each unknown variable is given as xi equals 1 over determinant of A times this determinant. So A11, A21, AN1, A12, A22, AN2, and then observe this carefully. Find the ith column of the determinant. So A1i, replace it by B1. A2i, replace it by B2. Yeah, so this is a substitution operation. You don't keep the original term A1i, A2i, and so on. Keep replacing this by the elements of the right hand side, Bn, and then the rest of the determinant stays the same all the way up to A1n, A2n, Ann. So this whole operation, we can write it in shorthand as AI over A, where the determinant AI basically means that you're substituting the ith column of that determinant by the right hand side, or the elements of matrix B, and this is known as Cramer's rule. in reality these two are identical. If you care to write this whole thing down symbolically, and you can show that this works out to be this exactly. So each element of this x will work out to be adjoint of A over determinant of A times the matrix B, which will work out to be this. Now again, what happens if the denominator is 0? So special case, if A equals 0, well, again, look at the numerator. If any of the numerators is also 0, inconsistent set of equations, there is no solution. I'm sorry, if any of the determinants in the numerator is non-zero, it is inconsistent. If all ai's are 0 for all I, the system is consistent and it has infinite solutions. So we have looked at two methods to how to solve a system of simultaneous linear equations in n unknowns for the non-homogeneous case, which means that at least one of the elements of your right hand side, the B matrix, is non-zero. Now the only thing to look at that is remaining is the homogeneous system. Which means that every single one of the right hand side is 0. Again, we can look at it using this method. For example, if the determinant of A is non-zero, there is only a trivial solution, which means every single variable x1, x2, all the way to xn is 0. But if the determinant is 0, then there is an infinite number of solutions. So these are the two general methods to find out the values of the unknown variables x1, x2, all the way through xn. And so let's take a solved example to better understand how to work these methods. So let's say solve this system of equations. So we have x plus 7y minus 3z equals 11, 25y plus z equals minus 3, and 3x minus 6y plus 2z equals 0. Now as soon as you have a set of equations given to you, there are a few things to check. So first of all, how many unknowns? So x, y, z, 3 unknowns, and you have 3 equations in 3 unknowns. So the number of equations is equal to the number of unknowns. Now the right hand part of this set of equations, so 11 minus 3, 0. So clearly it is not a homogeneous system because you have these non-zero elements on the right hand side. The next thing to check would be this determinant, so this part, Ax equals B. So let us first write it in that form. So A would be 1, 7, minus 3, for here it's 0 times x, so 0, 25, 1, and 3 minus 6, 2. This is your A matrix times the variable matrix, in this case x, y, z, equals b, which is 11 minus 3, 0. So after writing it in this form, ax equals b, the next thing to check is whether this determinant a is 0 or not. So check this calculation. So 1, 7 minus 3, 0, 25, 1, 3 minus 6, 2 works out to be 1 times 56. I'm expanding by this column. Note that if any column or row of the determinant has one or more 0 elements, it's always easier to expand by that row or column. So that's why I'm choosing to expand by this column instead of by any other row or column. So 1 times 50 plus 6, so 56, minus 0 times something, the cofactor of this element, which we don't care, plus 3 times, so 7 minus 75, so 82. So the value of the determinant of A works out to be 302, which is not 0. So which means we can find out these unknown values. So because we are taking this as a worked out example, I want to demonstrate this by both methods. So let's first try to find out the values of x, y, and z by the matrix method. So using the matrix method, well, x, y, and z you need to find out as A inverse times B using this definition. And to do that, you first need to find out A inverse. So that is adjoint of A times B over determinant of A. And for calculating the adjoint, you need to find out the cofactors of each element of A. And so let's take an example to recall. C11 is minus 1 to the power I plus j, so 1 plus 1, and then you block this off, so 50 minus 6, so 56. And so on. I'll leave it as an exercise for the reader to calculate each cofactor, and what you can show is adjoint of A is basically the transpose of all the cofactors of the elements of A. Works out to be this. So 56, 4, 82, 3 minus 7 minus 1 minus 75, 27, and 25. So A inverse is simply adjoint of A divided by the determinant of A. So 1 over 302 times this whole big matrix. I'm not going to write it again. And then once you have A inverse, you get your unknown variables x, y, z is A inverse times B. Well, I'll write it here. 1 over 302 times 56, 4, 82, 3 minus 7 minus 1 minus 75, 27, 25 times your right hand side matrix, which is 11 minus 3, 0, and you can do this calculation and it works out to be, let's still keep this outside, 1 over 302, and first do the multiplications here, and you can show that this works out to be 604, 0, minus 906, which finally gives you x is 2, y is 0, and z is minus 3. So this is one way to find out the values of x, y, and z.